We are speaking today about types of numbers or sets of numbers. The first kind is natural numbers. Natural numbers are counting numbers. 1, 2, 3, 4, 5, 6, blah, blah, blah. Notice that 0 is not a natural number. We're talking about whole numbers, and whole numbers have all of the natural numbers, so 1 to blah, blah, blah. But they also include 0. So whole numbers are counting numbers including 0. And now moving on. The next type of number we have are integers, right? Now integers, if you look at this number line here, all of the numbers in this line are integers. So you have all the natural numbers 1 to infinity, and then you have 0 as well. So you have the whole numbers. So you have all the natural numbers, you have all the whole numbers. But now with integers, we have negative numbers as well. So integers are natural and whole numbers, but they also include negative numbers as well. And this is the sign for integers. And you see these signs, that special Z and that W and that N, you need to know them signs. Trust me, right? You're gonna see them things often. Right. The next type of number we have are rational numbers, right? Now, you notice that we had the natural numbers, which was counting numbers, 3, 4, and then we had the whole numbers, which included 0. But you notice neither of these had any negative numbers in them, ... It means it goes to infinity, right? And then we had the integers, which now have some negative numbers in there. But between those numbers, we have fractions, like it have 1.5 over here, and that kind of thing, right? So let me just say you have 1.5. 1.5 is 3 on 2. So 3 on 2 will land somewhere right there. And look, we see in it here. Well, we see in a half between 0 and 1. We see in 5 on 2, which is 2.5, right? So with rational numbers now, we're talking about fractions. And look, we even have negative fractions here, -0.5 or even -2.5, right? So fractions are rational numbers. But if you look at it here, rational numbers are fractions involving one integer over another in the form P over Q. So you see I have two numbers, a numerator and a denominator, but individually these guys are integers. Yeah, they could be negative, they're natural numbers, they're whole numbers, but they could also be negative. Yeah, so these are rational numbers, right? So rational numbers, I could have -3 on 2, and that is a rational number. Let me hear some dunnits. So we have rational numbers. Now we're going to irrational numbers, and irrational numbers are a bit special, right? Irrational numbers are those whose exact value we can never know. Yeah. So do you know, like, the square root of 2? Because the square root of 4 is equal to 2, and we'll talk about that. But what about the square root of 2? And we'll talk about what square root is just now. If you don't know what square root is, don't worry, right? But we don't know where is that. If you type in the square root of 2 in your calculator, and I'm gonna do it now. Where's the square root sign, boy? Square root of 2. What you get in the calculator is 1.414213562 ... and that goes to infinity. Nobody knows when this ends. So we don't actually know. It's not like it's a half, because a half is just 0.5 and we done. Yeah, a half is 0.5 and everything done. So we know the exact value of a half. We could measure 0.5, but we can't measure this. We don't know when it is finished. So we don't actually know the real exact value of the square root of 2. We have no idea, right? And I'd like you to write some of these down here. because these are some examples of irrational numbers. Some of them you might not know, like you might not know what E is. E is the exponent. You're supposed to know what pi is, right? And if you don't know what pi is, we will do it, so don't worry, right? You know how to study it. Right? Root of 2, root of 3, the ln of 2, pi to the power of n. We don't know any of these numbers. We could only approximate them. Let me hear some donuts. So we have what? Let's just do a recap. Natural, whole, which includes 0, negative, which includes negative numbers, not negative, integers, which include negative numbers, rational, which are fractions, irrational, which is we don't even know what that is. You know, we have no idea what those guys really are. And then we have real numbers, and real numbers, well, them is just everything. Real numbers is the set of all numbers, right? So I should have put R. I know I would have seen some kind of mistake here. Real numbers, well, not R, actually is correct, because I'm referring to real numbers as a set. So real numbers is the set of all numbers, yes. So you can see here in this diagram, we have the natural numbers 1, 2, 3, 4, and all of the natural numbers are, well, this diagram missing whole numbers. So it's supposed to have whole numbers here, which includes 0, and then we have integers, and then we have rational numbers, and then we have, well, irrational numbers, and then we have real numbers, which is just everything. So everything we just talk about is a real number. Everything. Yeah? So you have to know all of this stuff. It seems easy one at a time, but when it starts to pile up, you know, and I ask you, you know, Sarah, what is a real number? And Sarah's supposed to say, well, any number is a real number. Well, almost any number. Right? Now, these are the types of numbers that we have to know for Csec. There are other types of numbers. It have a number called complex numbers, right? And we do have to know this for Csec. But complex numbers, and I just letting you all know, is small I, and that is the square root of -1, which technically does not exist. You cannot have the square root of a negative number, right? So that doesn't exist, but we use it in maths. So there are complex numbers, but thankfully we don't have to do that for Csec, right? Right, so we're talking about here identity of operations, and this is interesting. Remember, operations are addition, subtraction, multiplication, division. Right, so the operations are addition, subtraction, multiplication, and division. And remember, we was talking about how addition and subtraction is kind of the same thing, and multiplication and division is kind of the same thing. So it really just have two operations, right? But then multiplication is repeated addition anyway, so it just really only have one, right? So we was talking about that. But now each operation has its own identity. So what does identity mean? The identity of an operation leaves the original number unchanged. What does that mean? So let's talk about the operation addition, right? So for addition, we see that we have the number 4. But if we add the number 0, right? That 4 remains unchanged. Nothing happened to the 4. Yeah? So we have a negative 4, and if we add a number 0, or even if we minus 0, nothing will happen. The number remains unchanged. So we say that 0 is the identity for addition. And if my handwriting is scrappy, please let me know if anybody can understand that. You know, teachers and doctors have horrible handwriting. So there is an identity for multiplication, and it's not 0, because remember, if I take 8 times 0, the answer is 0, so I definitely change the 8. Yeah? But if I take 8 and multiply by 1, well, that doesn't do anything. The 8 remains unchanged. If I take negative 8 and multiply it by 1, or even divide it by 1, it remains unchanged. So, for multiplication, 1 is the identity for multiplication. Let me hear when you're done it. So then we're talking now about the inverse of a number, right? So the inverse of a number, so we had the identity of an operation, but this here we're talking about the inverse of a number. So the inverse of a number combines with the combined with the number. No, it is combined. I was right the first time. Yes, I should trust myself. The inverse of a number combines with the number to give the identity. Right? So the inverse of a number combines with the number to give the identity. So this is through some operation, whether it be addition or multiplication. Right? So, for example, in addition, right, I have the number 5. If I add that to -5, I will get 0. 0 is the identity for addition. So since I add 5 to -5 and I get 0, we could say that -5 is the inverse of 5, right? So we have 5 plus -5, and if we have -2 and we add 2, then we'll get 0. So we could say that 2 is the inverse of -2, because once we add them, we will get the identity. Now for multiplication, the inverse is a bit different. So you can see here for addition, if the inverse has a different sign, once the inverse has a different sign, it'll be the inverse, right? But for multiplication, it's not about the sign, it's about fraction. Because if I take 6 multiplied by 1/6, I will get 1. So 1 is the identity for multiplication. And so therefore this 1/6 is the inverse. So 1/6 is the inverse of 6 for multiplication. For addition, -6 would be the inverse of 6. Right? So it depends on the operation you're talking about. So we can see here a half multiplied by 2 will give me the identity for multiplication. And so 2 is the inverse of a half. Let me hear when you're done it. So the thing is that with the inverse of a number, right, when it comes to multiplication, we also refer to it as the reciprocal or the multiplicative inverse. Yeah, so 1/6 is also referred to as the reciprocal or the multiplicative inverse of the number 6. For multiplication, and this is an important thing just to note, when you multiply by 0, you just get 0. No matter where you multiply by 0, you get 0. But for division, when you divide by 0, the answer there is undefined. Some people just like to say it's infinity. Even the textbook had infinity. I personally agree with that. I personally agree that anything divided by 0 should be infinity. But the truth is, we just don't know. Nobody has ever proved that something divided by 0 is infinity. So the truth is, we don't know. And so when you reach here in our maths problem, the answer is undefined. Yeah? So let me hear some donuts. So we reach some laws here now. Now these laws that we are about to do here are laws that will come up to bite you in algebra. You see, all of these things that we've done today, everything that we've done today will be heavily involved in algebra, right? Your understanding of algebra will depend on this stuff. So the first thing we have here is the commutative law. And the commutative law refers to the order in which an operation is performed. So for addition and multiplication, if we look at 2 plus 6 plus 9, that is the same or equal to if we had 9 plus 6 plus 2. In fact, I could have added the 2 to the 9 first and then add the 6 after if I wanted to. You could add this in any order and you will get the same answer, right? Same thing for multiplication. If I take 2 times 3 times 5, that is the same thing as saying 5 times 3 times 2 or 5 times 2 times 3. You know, you will always get the same answer. So we could say here that addition and multiplication are both, oh, not both doesn't have an E. What's wrong with me? Both commutative. Sorry for the handwriting. I'll try to do better on this side. If you look at subtraction and division, however, you will see that 7 minus 2 is what? 5? But that is not the same as 2 minus 7, which is negative 5, right? So these two are not the same, yeah? 8 over 2 is not the same as 2 over 8. So therefore, subtraction and division are not commutative. Subtraction yes, yes, very good question. Division, I forget how to spell division. Yes, right. But yes, so this is an equal sign and this is a not equal sign. So it means that they are not equal. Very good question there. Subtraction and division are not commutative. Right, so we talk about the commutative law, and that means order, right? So we could see addition and multiplication, you could be in any order. Subtraction and division, not that much, right? Now we're talking about the associative law, and the associative law is something similar to the commutative law, but this deals with the grouping of numbers, right? So in addition and multiplication, what we could see is if we had 3 plus 4 plus 7, what we could do is we could group the 3 and the 4, add them first, and then add that to the 7. Or we could group the 4 and the 7, add that first, and then add that to the 3. But no matter how differently we group, we'll always get the same answer, right? Same thing with multiplication. If we multiply the 2 and the 4 first, and then the 5, it'll be the same as if we multiply the 4 and the 5 first, and then the 2. So we could say that addition and multiplication are associative. And we can see here that that is certainly not true for subtraction and division, because if we do 9 minus 5 first and then minus the 2, right? 9 minus 5 is 4, minus 2 is 2, right? That will not be the same as if we did 5 minus 2 first is 3, and then 9 minus 3 we end up get 6 on this side. So these two are not equal, right? So same thing with division. If we divided 8 by 4 first and then divided that by 2, it will not be the same as if we divided the 4 and the 2 first and then have that divide 8. You know, that is not the same. So subtraction and division are not associative. Associative. Let me hear some donuts. Take your time. So we have the commutative law, the associative law, and the last of the laws are the distributive law. And this is something we'll use very, very often. The distributive law deals with multiplication of numbers in brackets. So if we have 3 multiplied by 4 plus 7, yes, BODMAS says do the brackets first and then multiply after. So we could definitely do that. But the distributive law says, well, we could do something else too. We could have the 3 outside the brackets, and you notice I do have a multiplication sign. So that multiplication is actually understood. We could also put a dot here. So I could put 3 dot 4 times 5, and it means multiplication, right? So we have many ways that we write multiplication. And what this means is the 3 has to multiply by the 4, or the 3 have to multiply by the 7. The 3 has to multiply by everything that's in the bracket. So we get 3 multiplied by 4 plus, because this plus here, 3 multiplied by 7. And well, the answer there is 33. Right? So you can see we have another example of the distributive law when it comes to negatives. So when you have the 4 times 8 and you have 4 times negative 3, you could think about this in 2 different ways, right? You could think about it as, well, 4 times 8 plus 4 times negative 3, so you notice the negative is here, right? Or you could think about it as 4 times 8 minus, from this minus here, 4 times 3. Both of them are correct, right? So you notice the negative is not here anymore. The negative is now here. So they both have one negative number, right? So in this case, 4 8s are 32 plus 4 3s are negative 12, because it's 4 times negative 3, right? And in this case, 4 8s are 32 minus 4 3s are positive 12. And they'll both work out to be the same thing, yes? So be careful with them negatives, and let me hear some dunnits. Take your time and write this one though. Thing that we know, oh gosh, I don't even how to teach this, so let's start writing one time. Now, the thing is that some of us mix up factors and multiples. Factors are the smaller ones, multiples are the bigger ones. So if I have, say, 10, the factors of 10 are 1, 2, 5, and 10. Right? These will multiply to give you 10. These can divide 10. The multiples of 10 are 10, 20, 30, 40. So these are the bigger ones, are the multiples. The smaller ones are the factors. Let me hear when you're done it, right? So the factors of a number are those smaller numbers that can divide exactly into that number, including 1 and the number itself. So the factors of 20 are all of these, and the factors of 40 are all of these. Let me know when you're finished. The multiples of a number are the products of that number with any natural or counting number. So 5 times 1 is 5, 5 times 2 is 10, so the 15, the 20. The bigger ones are the multiples. Let me hear done it. Very good. So we have factors, we have multiples, and trust me, factors, remember that when we hit algebra, factors are these two numbers, right? So factors are, like, say 5 times 4 will give us 20. So the two numbers that multiply, so, and this is something we'll see in algebra a lot. 4 times 5 is give us 20. But in algebra, they'll give us 20. And they will tell us, find the factors of 20. So they'll use the word factorize. And of course, it wouldn't be 20. It could be some x plus 3 plus whatever. And they're going to say factorize. And what they mean is that they want you to find the two other numbers that you could multiply to get that. It's simpler. It's kind of like simplifying in a way. You're simplifying 20. Right? 20 is really 4 or 5 times, right? So factors, factorize, keep that in your mind. We'll see it again very, very soon, right? Right, so powers. If the same number is multiplied repeatedly, we could use an index or a power to show how many times the repeat occurs. So, if I have 2 times 2 times 2 times 2 times 2, that is 2 5 times. It wouldn't be 2 times 5, No. 2 times 5 is something different. 2 times 5 is 10. Right? But 2 times 2 is 4, 2s are 8, 2s are 16, 2s are 32. Right? So this will be 2 to the power of 5, which is 32. Yeah? Or another example is 3 to the power of 4, which is equal to 3 4 times. Eh? Not 3 times 4, no. 3 multiplied by itself 4 times. Right? 3 3s are 9, 3s are 27. 27 3s are 81. Can the power or the index, which is this, be a negative number? Arisa, do you think that the power could be a negative number? But how could you, if I have 2 to the negative 5, how can I multiply 2 by itself negative 5 times? Right. The answer is yes, you can have a negative number. Yes, you can multiply 2 by itself negative 5 times, and we will see that in a very soon to come class, right? Very, very soon we will see what 2 to the negative 5 will be. But if it is you want to go and research it yourself, feel free to find out what will you get if you have 2 to the power of a negative number. Let me hear when you've done it. Then we have roots. And I have interesting things about roots. The root is the inverse of a power. Yeah? So if 2 squared is equal to 4, I could have the square root of 4. Right? The square root of 4, what does square root mean? You could think about a square root as a question, right? So if I have the square root of 4, the question I am asking here is, what number that if I multiply it by itself will give me 4? And the answer is 2. Right? Remember, 4 is actually 2 squared. So it's kind of like if the square root and the squared is cancelled. And this is an important thing to remember. Important thing to remember. We'll see this again. Yeah, none of these things are isolated. Right? So the square root and the square is cancelled, and you'll get back the number. So the square root of 4, what number that if I multiply it by itself will give me 4? The answer for that is 2. Right? Now, it's not just a square root. If I have 5 cubed is 125, I could also have the cube root of 125, which is the same thing. What number that if I multiply it by itself 3 times will give me 125? Well, the answer is 5. Right? Or 4 to the 5th power is 1024. Right? But if I can have the 5th root of 1024, which asks the question, what number that if I multiply it by itself 5 times will give me 1024? Oh, the answer here should be 4. So little mistake there. I'll probably have to fix that in the Google Classroom, but the answer there is 4, right? Now remember, 1024 is 4 to the power of 5. So the 5th root of 1024 is really the 5th root of 4 to the power of 5. So you can see that the root and the power will cancel. Yeah? And well, the answer here should be 4, right? Sorry about that. Even though it might be simple stuff. Now, with a square root specifically, we have a couple of tricks that we could do. Right? And it's important to remember these tricks when we reach algebra. So trust me, everything that we're doing today, you have to know it by heart when we reach algebra. And we'll reach algebra in like 2 classes, because after number theory, we're doing algebra. Right? So, roots, we have some tricks when it comes to multiplication and division specifically. It doesn't work for addition and subtraction, but for multiplication and division, they work. Right? That is because for multiplication and division, I could, you could treat this like one number. You could treat this like one number. So that is why it'll work for multiplication and division. But for addition, if I had 9 minus 36, that is two different numbers. So it doesn't really work that well, right? But 9 multiplied by 36 multiplied by 64, what is the square root of all of that? Right? Well, instead of going and point, what if you didn't have a calculator? Yeah, what would you do? Right? You would want to multiply all of these things and then find the square root? No. Right? So what you would do is you would realize that, hey, these are all squares. Right? What we call square numbers, and we'll see that just now, what we mean by square numbers. Right? But they're all square numbers. So 9 is really 3 squared. 36 is really 6 squared. And 64 is really 8 squared. So this is the trick. If you could express these numbers as a square, then you could actually split up the roots. Alright, so we get now the square root of the square root of 3 squared multiplied by the square root, and now the roots cancel. So it just becomes 3 times 6 times 8, and it's 144. So instead of busting your brain to do this, if you had known that you could just split up the square root sign, to the individual numbers and see if they could square, and then cancel the square root sign. That is a method that we like to use. Yeah, we like to use that method. And it also works for division if you have a fraction. If you have a fraction, you could actually split up the square root sign. So you see the square root sign is over the whole fraction. Well, we could split it up here over the numerator and the denominator. This is an important thing because in algebra, you're going to see the square root of x over y. And then you are going to have to remember that that is the square root of x over the square root of y. Yeah, that they are the same. So these are important things to know and remember, right? So please study this stuff, right? So you can see that the squares here cancel because 36 is really 6 squared, 64 is really 8 squared. The squares cancel, leaving me with just 3 over 4 or 0.75. Let me know when you're done it. Now we have here square numbers, and yes, you are going to have to draw these diagrams. Yes, please, right? What is a square number? Well, numbers that can be represented as a square of dots. If you could represent a number as a square of dots, right? That is, the product of a number by itself gives a square. So like how I was saying 9. 9 is a square number because it's really 3 squared. So I could have a square with 3 times 3 on either side. Yeah? So you can see here 3 times 3 and I have 9 dots. So 4 times 4 is 16 dots. So 16 is a square number. Please note that 1 is a square number because 1 squared is 1, right? You can have a square one side by one side and you will still get 1. So draw the diagram, please. These here are the set of the first set of square numbers. So not all numbers are square numbers. 3 isn't a square number. Like 2 isn't a square number, right? It's not a square number. So so these are all of the square numbers there, the numbers that have a even square root, an integer or a whole number as a square root, right? Let me hear when you're done it, and yes, draw the diagrams, please. Rectangular numbers. Now at the end of the day, where is my pen? Oh, look at it, right? At the end of the day, if I have 10, alright, like let me just say 4. I could represent that as a square 2 by 2, right? 2 by 2 is a square number, 4, right? 4 is a square number. But if I had 6 isn't a square number. It doesn't have you know, a number that, well, it does, but it'll be a decimal, you know, because, you know, 2 2s are 4, 3 3s are 9, right? So between 2 and 3 somewhere there will be the square root of 6, right? But 6 does have factors. 2 times 3 is 6. So I could represent 6 as a rectangle. A rectangle 2 times 3, right? Or what about 20, right? 20 could be a rectangle with 5 times 4, or it could be a rectangle with 10 times 2, you know. So 20 is definitely rectangular, right? So once you have factors, then you could multiply those factors or arrange them in a rectangle. We call them rectangular numbers, numbers that can be represented by the shape of a rectangle. So we have the number 2. The number 2 is not a square number, but it is a rectangular number. Or the number 6, or the number 12, or 20, or 30, right? They are rectangular. The factors can be used to form a rectangle, right? So 3 times 4 gives us 12, right? Note that the number 1 is not rectangular. 1 is a square number, but it's not a rectangular number. However, all square numbers are also rectangular numbers. You know why all square numbers are rectangular numbers? Right? 4 4s are 16. That's a square number. But this is also a rectangular number because, and I'm sure some of you guys probably didn't know this, a square is a rectangle, right? A square is a special type of rectangle, but that is what a square is. A square is actually a rectangle, but guess what? A rectangle is not a square. Yeah, so we could do that later on when we reach geometry. So all square numbers are also rectangular numbers except 1, right? Draw the diagrams as well, please, and let me know when you're done it. Nice. So we have square numbers, rectangular numbers, and finally triangular numbers. And you guessed it, a triangular numbers form a triangle when expressed as dots. The question is, because we have the first 6 triangular numbers, 1 is a triangular number, yes, right? Because we need 1 to form the next triangular number, the second triangular number, which is 3, right? But we can't use 2 dots to form a triangle, so 2 is not a triangular number, right? 1, 3, the third triangular number is 6, the fourth triangular number is 10, right? The fifth one is 15, and so on. The next one is 21, right? So the questions become, can you find the 7th triangular number? Or can you find the 50th triangular number? Right? And these are questions that I'd just like you to think about. I'm not going to answer these questions yet. We'll answer these questions later down. Soraya and Caitlin, you guys are supposed to be able to find out what the 7th or the 50th triangular number is, right? But I ain't gonna ask earlier, so don't worry. Let me hear when you're done it. We have prime numbers, right? And a prime number can only be divided by itself and 1. For example, 5 is a prime number. And prime numbers are a mystery because we have no idea how many prime numbers there are, right? And we've been looking for patterns to try to find out how many, but we can't find any patterns. Prime numbers just seem totally random. But 5 could only be divided by itself and 1. 5 can't be divided by anything else without a remainder, right? So therefore it has no other factors. A prime number is not rectangular. I mean, yeah, I could say that with 5, I could make a rectangle 5 and 1, and that's a rectangle, right? But at the end of the day, let me just say 88 is a prime number. I don't know if 88 is a prime number, but let me just see. I know 88 could be divided by 11, right? So let me just see 73. So I think 73 looks very prime-ish, right? So let me just say 73 is a prime number. It makes no sense drawing a rectangle 173. You know, it have no other factors, so it makes no sense doing that, right? So at the end of the day, prime numbers are not rectangular, right? The number 1 is not a prime number, because a prime number could be divided by itself and 1, right? So 1 is not included as a prime number, right? 2 is the only prime number that is an even number. All of the other prime numbers are odd. Yeah, well, so far we don't know. We actually don't know, right? Maybe somewhere far down the line we could find another even one, but so far 2 is the only even one. The prime factors of a number are those factors which are also prime. For example, 6. The factors of 6 will be 2 and 3. 2 times 3 is 6, right? So these are the factors of 6, but 2 is a prime number and 3 is a prime number, and so these are prime factors, right? So now we're talking about approximation, and we're talking about decimal spaces. And first we'll talk about decimal places, or DP, right? So I have a number here, 124.09781, and we want it to 4 decimal places. Well, we know to 4 decimal places we had to count 1, 2, 3, 4, and then we had to check the number after. If the number is greater than 5, we round up, right? So this number is not greater than 5, so we keep it as 8. So 1, 2, 3, 4 decimal spaces there. If we wanted 3 decimal spaces, we count 1, 2, 3, so we can see that is 7. But we look at the number after, and if that number is greater than 5, it is greater than 5. So we have to round this 7 up to 8, right? So this is decimal spaces, and of course to 1 decimal space, we can see that 1 decimal space is 0. But we have to look at the number after. Well, that number is greater than 5, so we have to round that 0 up to 1. So decimal spaces, something that we're familiar with. And then we have the phenomena of recurring decimals. Now with a recurring decimal, for example, 1/6. Now you notice we have many different equal signs, right? This one means equal, and then this one means not equal. But now we have this one, which means approximately equal to. So this is what we would use for an irrational number, like pi or the root of 2, where we don't actually know what the value is. We will say it's approximately equal to that, right? So 1/6 is approximately equal to 0.1666 recurring. So that 6 is going to go to infinity. So that is approximately equal to 0.16 with a dot on top of it, because the 6 is going to be repeated till infinity. But if we look at this example, 3/11 is approximately equal to 0.27272727 to infinity. So we can see that both the 2 and the 7 are repeating, so we put the dots over both of them, 2 and 7. Nice? So that the 2 and 7 will repeat. Significant figures, and do not mix up decimal places and significant figures. With decimal spaces, we were looking at the guys after the decimal space. But with significant figures, we're looking at everybody. Everybody, right? So at the end of the day, I have this number here, 105.8054. If I wanted to 6 significant figures, I have to count, well, from the top, 1, 2, 3, 4, 5, 6. And then I have to look, I have to do the whole same rounding up thing. I have to look at the number after. That number is less than 5, so I don't need to round up. So this is what I get. 5 significant figures, I'm going to look at 1, 2, 3, 4, 5. Well, that number is 0. And the number after is 5 or greater. So I definitely have to round up that 0 to 1. So this here is 5 significant figures, right? 3 significant figures. We'll take a look at this one. you'll see that this one doesn't involve any decimal places at all, right? 3 significant figures is 1, 2, 3. And I still have to look at the number after, and if it's greater than 5, then I round up this number so I get 106. But then I also have 2 significant figures. So 2 significant figures are just looking at this one and this one. And well, of course, that is 1, 0, right? But at the end of the day, I have to look at the number after. If it's 5 or greater, well, then I round this 0 up to a 1. So it becomes 110 to 2 significant figures. And then if it is that I want the same number to 1 significant figure, I look at this number here. That's just 1, right? And I'll look at the other 2. Well, this one here isn't greater than 5 or 5 or greater, so I don't have to round it up. So I end up getting 1, 0, 0. So these zeros are not considered significant. Well, actually no, they are considered significant. If it is that I had 100, alright, these zeros are significant because these zeros are taking or keeping the place of the tens unit and the units and the tens and the hundreds, right? So these zeros are that. But if I had zeros before that, these zeros would not be significant unless you had some real number over here, you know? So you cannot start. If you start in with zeros, then those zeros will not be significant, right? So we have decimal places, recurring decimals, significant figures. Let me hear when you're done. Are the multiplication tables. Nice. Now they do not teach this in school. This is not a Csec thing at all. But I think that it's a very magical thing, and I think that everybody should know about it, especially my newer students, right? These are your multiplication tables. You have your 2 times table, 3 times table, your 4 times table, your 5 times table. All of these multiplication tables we had to learn. But did you know that there is a hidden, and I'm sure I teach people like Caitlin and Soraya this already, right? But there is a hidden pattern in your multiplication tables, right? So for example, take the 3 times table, for example. We have the 3 times table here. If you want to find the hidden pattern, what you do is every number that have more than 1 digit, you add up the digits inside of it. So check it out, right? For the 3 times table, we have this nice hidden pattern here. So we have 3, 6, 9, but then we add up 2 and 3. Well, that is 2 and 1, that is 3. 5 and 1, that is 6. 8 and 1 is 9. And then 2 and 1, that is 3, 6, 9. 3, 6, 9. And that's just going to go to infinity. Yeah? So believe it or not, all of these multiplication tables have this sort of pattern in them, and it's a very magical thing when it comes to numbers, right? Because we never explore this, but this is crazy. This is crazy that we have these magical little patterns inside of here, right? So if we check, all right, the 6 times table, right? So we could have the 6 and 3 and 9 are very, very similar to each other. So we can see we have 6, 3, 9, 6, 3, 9. 4 and 2 is 6. 4, 8, 9, 10, 11, 12. So 4 and 8 is 12, but 2 and 1 is 3. Yeah? So you always keep adding the digits until you reach to a single number, right? So 5 and 4 is 9. So this one have a different pattern of 6, 3, 9, 6, 3, 9, 6, 3, 9, 6. 6 and 6 is 12, and 2 and 1 is 3, 7, 8, 9. Yeah? Let me see if it have a pattern in the 5 times table now. Well, that's 5. 1 and 0 is 1. 5 and 1 is 6. That is 2. 5 and 2 is 7. That is 3. 5, 6, 7, 8, 4, 9, 5. 5 and 5 is 10. 1. and 6. Well, look at our pattern. Check that pattern out. And you all seeing our pattern there? Check this out. 1, 2, 3, 4, 5, 6, and that going down the line. And then on this side, I have 5, 6, 7, 8, 9, and 1. Crazy pattern, right? Yeah. All of these have patterns, and my favorite pattern of all is the 9 times table, right? So the 9 times table, if you add all of the numbers up, 9, 9, 9, 2 and 7 is 9, 3 and 6 is 9, 5 and 4 is 9, 4 and 5 is 9, 6 and 3 is 9, 7 and 2 is 9, 8 and 1 is 9, 9. 9 and 9 is 18, 8 and 1 is 9, 108, 8 and 1 is 9. So 9s, any multiple of 9, the digits will add up to 9. And that is crazy. Yeah, all of these. So I would invite everybody to look at your multiplication tables and see if you could find the patterns for the rest of them, right? And today we did a lot of work, and I didn't really give Ali any homework because the stuff that we did is really just stuff that you had to remember. But this is a nice little activity for you, and this is not a Csec activity at all, but it's real cool, especially if you have kids or you have family who, you know, in primary school and things. You could show them this, and this will blow their mind. Yeah, this will totally blow their mind, right?